continuing now with the lecture series on electric machine design. We're going to look at some issues regarding reluctance synchronous machine theory as we continue our study of RSM machines. This is lecture number 24, and I'm Jim Hendershot again. We see a picture here, a cutaway of the ABB machine, which we got off the web, so you can clearly see the stator core without any windings in it. They've left those out, I guess, so you can see what the rotor core looks like. And it's clear there that the RSM starts with a standard induction motor, stator lamination, and winding. And the slot numbers seem to work out okay for the three-phase coil arrangements, which are identical. I suspect they haven't changed those at all. I imagine they're even using maybe the same number of turns per coil right off the production line. This leads us to the conclusion that based on ABB's theories, that IM frames and mechanical components of standard induction machines are very useful with little or no modifications necessary, which leads us to optimize the rotor. Happily, no magnets are required, although they're optional. There's no conductors, no intentional currents flowing in the rotor. Even eddy currents are unwelcomed. The only task moving forward is to develop a rotor that must produce a good factor of salience in order to be attracted by the rotating electromagnetic stator pulse. This is a photo taken from the ABB website, and we've blown this thing up so you can see what this is apparently what their lamp looks like. Notice they got 4 keyways in the bore, and they put those 4 keyways right in line with the Q axis. I suspect that's intentional. That probably reduces the inductance in this axis, because this is a flux carrier and it attracts right to the shaft. So by putting a little gap there, you've added more air in this axis. So these little ribs here and these little ribs here are there to hold this rotor together, as we said in the last lecture. But those reduce your salience ratio, because until those are saturated, the flux is happy to go through those sections. So these are the carrier webs, flux barriers, and flux carriers. So what goes on inside of a machine? Let's go back to our example we did several lectures ago, showing a simple stack of laminations with a coil wrapped around it and a DC power supply here. And then the piece we'll take and cut a big piece out of this part of the core and mount it on a shaft, put bearings on it, and we even studied this before. When we energize this coil, there's a magnetic field set up, and it tries to jump across this air gap. It takes ampere turns to do that, and if this rotor piece is horizontal here, such that the quadrature axis is lined up with the stator, then the inductance is very low, and the current builds up very fast when the voltage is connected across here. But that creates magnetic lines of flux that go around here that want to jump across that air gap, and they're going to attract this thing. So that there's a big attracting force that we discussed earlier there that puts a moment of force on this, a torque, and this rotates. And as it rotates, the inductance in the circuit that used to be very low, it's increasing as we align this thing up. And so when it's all lined up, the inductance is maximum there. So there's a big difference between the salience ratio and the inductance ratio, and they're distinctly tied together by the and they're tied together because they're one and the same, and they're determined by how much air we put in the circuit when we were in this axis versus in that axis. As we've said, the RSM torque dependence is dependent upon this. You see, this is really a more clear example. It kind of shows a switch reluctance rotor inside of an induction stator, but it gives you a much clearer picture of the effect of saliency. Here's your direct axis here, and there's your quadrature axis, and that's how this picture from our previous slide translates into this. In a rotor, it's got 4 poles instead of 2, and as this rotates, your inductance goes from maximum to it's maximum in the direct axis and minimum in the quadrature axis, and you see that sort of going to be a kind of a sinusoidal inductance wave shape there. The equations that describe the DQ equations that describe this this situation, since we're using the same stator and inverter, the windings are for the most part sinusoidally distributed in the stator. So the stator leakage inductance is different than that from the induction motor. So the air gap flux harmonics are handled with an additional term using Park's equations. The conventional equations of a synchronous machine are converted to the equations that describe the behavior of the RSM. This is a synchronous machine as well. Since there is only a single magnetic circuit, there is no excitation field term like you would have with an induction machine. So we have the DQ equations for the RS machine. And here's the legend. Here's our DQ equations. And whoops. And the as far as power factor is concerned, we've already stated we have to have good power factor. The need for a good power factor is recognized so as not to require an oversized converter. RSM machines over the past have had limited success competing against other machines because of this limited power factor, as we've said, and that's the culprit is a low saliency ratio. And the power factor of the RSM is given by the cosine of. In the rotating reference frame, the voltage, the D and the Q axis voltages are steady state voltages. The MF angle is represented by this term here. So the power factor is calculated from the cosine of this angle. The torque equations are represented by this formula. The electromagnetic torque of a reluctant synchronous machine is the same as for a synchronous machine, but it certainly is related to the D and the Q axis currents. The D and Q axis values depends on the size of the machine, the total number of conductors in the stator. Of course, the two inductance values vary with the square of the number of turns in series in the machine measured line to line. These two inductance values vary with the square of the turns in series, the turns in each coil in series. The inductance ratio depends on the saliency ratio of the RSM. More about that coming up, which is set by the amount of air, which is equivalent to the flux barriers, and the amount of steel, which is equivalent to the flux carriers in the magnetic circuit of the coils it's linked with. Coils or phases it's linked with. So the question is, can the RSM produce sufficient torque density to compete with other machine types? And ABB has recently, as spring 2012, announced a broad RSM product line and claims the answer is yes. So what we're going to do is to see what we have to, what's necessary to achieve such a possibility. And we can thank Tom Lippo and Mr. Matsuya and Gary Horst, who have blessed us with their work with RSMs as back as 1954 to provide us with a good starting place for designing an RSM rotor. They've answered this question that we posed as to the relationship between the power factor and the RSM machine. If they have done extensive simulations, and Lippo Professor Lippo and Matsuo at Madison, University of Wisconsin, have done extensive calculations and simulations, and Gary Horst, an engineer from Emerson Electric, has backed up their simulations with building samples and testing them. And here's what they've found: a relationship between the power factor and the saliency ratio is based on their work. So this is a plot of all the models that they simulated. They plot power factor versus saliency ratio. And you can see here as a target for all of us, if you achieve a saliency ratio of 7-to-1, or an inductance ratio of 7-to-1 between the Q and the D axis, this equates off of this curve of a power factor of 0.8. And 0.8 is certainly an acceptable power factor to compete with an induction motor. So that tells us what our design goal is. The work summarized by the previous slide indicates possibilities for this machine against an induction machine. Since the infrastructure components are identical and the power converters are similar to IEM products, this makes a very exciting opportunity. Now, a study of previous designs of RS machines over the years indicate difficulty in achieving saliency ratios above 3.5-to-1. Lippo and Matsuo of the University of Wisconsin have created rotor configurations with acceptable ratios that have been validated by Gary Horst. The two principal known ways to create this kind of saliency in an RSM machine involve laminating either axially or radially, as we saw in the previous sketches, with alternate flux barriers and carriers to control the permeability paths to create the poles, the salient poles, we should say. And these are those two examples that we've seen before. Now, tests have shown that this method of laminating gives you the highest saliency ratios. However, the complexities of designing this are very tough. You have to have a lam dies or punching tooling that forms every one of these, and every one of these is a different radius. They have to fit together. You could automate the assembly, but the tooling required to make all these different parts is significant. Someone has proposed taking and making two coils of a coil of steel and a coil of an insulating material like a nylon or a Teflon or some other carbon fiber material or something like that, and wrapping these up together like a spool of masking tape and bonding that spool together somehow and then cutting it into pieces. So if you have a complete circle, you could get 4 pieces out of them that become these 4 assemblies. That might be a reasonable way to do it. These examples were made with each one tooled separately, and the first ones like this I've seen were built by Professor Tim Miller at the University of Glasgow in the SPEED Consortium, and they used a non-magnetic piece here and drilled holes and tapped the core, and so they had fasteners here to clamp all this together. Well, that's not a viable production technology. A more viable production technology is to laminate them this way, because if you do it this way, you throw the core, you throw the hole in the stator away, and that's expensive silicon steel, so you throw that away. This way, you punch it out of there just like you would an induction motor. If you're going to compete like an induction motor, it seems like you have to laminate it this way, but you have to get the saliency ratio with this type of a construction as good as that one. Now, apparently that's what ABB has done. Not sure. That's for the rest of you to decide and to figure out. Of course, there's the mechanical considerations in terms of trying to hold this thing together, because there's not only radial forces on those flux carriers, there's also tangential forces on those flux carriers. So all those issues have to be figured out, and those present some opportunities and challenges. The bottom line is this is a great opportunity to be creative and inventive, to come up with a good rotor design. In passing, as we end this lecture, I want to point out a special version of this that was done by Padova, University of Padova, how you pronounce it. And this shows layers of magnet slabs put in in here to be used as flux barriers. So I find that kind of interesting, but they would have to be magnets that were low enough in cost to justify doing it. But I think in the literature you're going to find lots of examples where people enhance these. Rather than spend their R&D efforts and their time and their simulation hours and their tools spent, they're playing around with putting magnets in to increase that performance of their machine. And my view is that don't waste your time with magnets. Concentrate on a very unique rotor barrier carrier configuration that gives you the saliency ratio of 7 to 1. That concludes this lecture.